This is Jack Jackson. Today we're going to be investigating the Pythagorean Theorem. The Pythagorean Theorem is probably one of the most famous theorems in all of mathematics, certainly in all of geometry. And we're going to actually prove the Pythagorean Theorem as well as state it today. And I'm actually going to show you two different proofs. There are probably over 100 different proofs of the Pythagorean Theorem. It's such a popular theorem. And I'm going to show you two of them. The first one I'm going to show you is a little bit unusual because it uses similar triangles rather than areas. Most of them use areas. Then the second proof is going to be one that involves some areas. So the Pythagorean theorem says, given a triangle with hypotenuse of length C and legs of lengths A and B, then the triangle is a right triangle if and only if A squared plus B squared equals C squared. IFF there stands for if and only if. Usually when people say the Pythagorean theorem, they mean it in this direction, that if you have a right triangle, so we start with the right triangle, then the sides must have the relationship called the Pythagorean relationship, A squared plus B squared equals C squared. But we'll also prove the converse in the second tab here. So here we start with any right triangle. Notice that this is set up so that it always stays a right triangle, but I can get any size right triangle I want. And what we're going to do is use our standard labeling here, and we're going to start by constructing the altitude from C, with the vertex where the right angle is, to the opposite side. And notice no matter how I adjust this, that comes to a point we're going to call D that's between A and B on that hypotenuse. Now let's let x be the distance from A to D, and then that makes C minus x the distance from B to D. And we'll call h the height of this triangle from D to C. So notice we have right angles, actually two right angles here at D, and a right angle for the bigger angle at C. Now what we're going to do here is we're going to notice that we have similar triangles here. Okay? All three of these triangles have a right angle here. Now let's look at the big triangle versus the medium-sized triangle. They share an angle at B. So therefore, they have to be similar triangles because they have two angles that measure the same. Similarly, the small triangle and the big triangle share an angle at A, as well as they both have a right angle. So they are similar as well. So in fact, all three of these triangles are similar right triangles. So all their angles are the same. So this angle right here is the same measure as the angle at B. And the angle at A here is the same as the measure of this angle from D to C to B. So let's look at angle B and find the sine of that angle. You could actually do this without knowing what the sine is, just by proportionality of the similar triangles, but we know what sine is. So the sine is opposite over hypotenuse. Let's do it from the big triangle. Then the opposite side for the big triangle would be side B, and the hypotenuse is this whole side C here. So that's sine of that angle is B over C. On the other hand, let's do it from the little triangle. This is the angle here that has angle B. So now opposite is this side X. And the hypotenuse now is side B. So side B was the opposite side from the big triangle, but it's the hypotenuse from the little. Okay, so anyway, that's x over b. Now I'm going to solve this for x by multiplying both sides by b, and we get x equals b squared over c. So these two fractions equal each other. That's called a proportion. Next, let's do the cosine of angle B, again from the big triangle. So the big triangle, the adjacent is A, the hypotenuse is C, so we get A over C. Now let's do, from the medium-sized triangle, do the cosine. The cosine would be adjacent over hypotenuse, and if you look how this one is oriented, the adjacent is the red side, which is C minus x, and the hypotenuse is A. So it's C minus x over A. Now I'm going to solve for x. I'm going to multiply both sides by a here to cancel out the a on the right, and I get a squared over c equals c minus x. add x to both sides, and then subtract a squared minus c to get x is c minus a squared over c. You might want to write those couple steps I didn't write down there. Now x is the same either one of these equations, so that means b squared over c equals c minus a squared over c. Multiply both sides of the equation by c to clear out our fractions. C's cancel here, giving us b squared on the left, and on the right we get c times c is c squared, and the c's cancel on this part when we distribute, and we get a squared. Add a squared to both sides, and we do get a squared plus b squared equals c squared, exactly what we were trying to prove. So there is a nice little proof, and it uses the fact that if you draw a perpendicular from the right angle vertex to the hypotenuse, you get 3 triangles out of this whole thing that are similar. Now I'm going to show you another proof that I think you may like actually a little bit better. So let's start here, and we're going to start with any right triangle that we want. Again, this is set up to be any right triangle that we want here. Now, standard labeling. Okay. Now extend this side of length A out an additional length equal to B, so that we have a straight line segment from C to B to E. So B is between C and E. Okay. Similarly, let's whoops, getting ahead of myself here. Wow, how'd that get way over there? Give me just a second here. Alright, got ahead of myself one step. So we're also going to consider a point where we extend out CA a length equal to A. So now both of these are line segments. D to C and C to E are both line segments of length A plus B. Now we're going to make perpendiculars to D, through D, perpendicular to this side, and then through E, perpendicular to this side. And we've got 3 right angles there, so that makes the 4th one a right angle. And in fact, we have a rectangle. Furthermore, on a rectangle, we always have opposite sides congruent, but this one time we have adjacent sides congruent as well. So in fact, we get that's actually a big square. Now, the next thing we're going to do is we're going to find points G and H. So we're going to go out a distance B here. Well, we'll call the point F where the other corner of the square there, they're the vertex. And then we'll pick a G between D and F so that it's B away from D. And then H between F and E so it's B away from F. And that means this other distance has to be A because both sides are A plus B. And notice this is dynamic, so I can adjust this to get any triangle size that I want. Okay, now what we're going to do is we're going to connect up some other sides here. And we're going to make this little green shape going from A to G to H to B back to A. That is a quadrilateral. Now, I'm going to claim that it's going to be a square, but we're going to have to prove that. Okay, so the first thing to notice is you actually have some triangles formed now. So you have a triangle in each corner. They all have side of length A. All the blue sides are congruent. All of them have a side of length B, so all the red sides are congruent. And the angle between them is a right angle, so all those angles are congruent. And notice what we have: side, angle, side, So by the side angle side postulate, all four of those triangles are congruent. Well, among other things, that means that their hypotenusae have to be congruent. In other words, the long side, the green sides, all have to be the same. This one down here was C, so they're all C. So now we know that our green shape is a rhombus. It's a quadrilateral with all the sides congruent. Now if we could just show we have a right angle here, we could show that it's actually a square. And we can do that. Well, one of the things that we also get is all these angles where the green and the red sides meet are all the same measure. Let's call that measure T. Okay, that's same as our original angle that we would normally call A there. Okay, next let's look at this one down here. Now in our original triangle, one thing we know in any right triangle is, well, any triangle at all, the angles add up to 180 degrees or pi radians. But in a right triangle, we already know that the right angle takes up pi over 2 radians, or 90 degrees of that, leaving only pi over 2, or 90 degrees, for the other two angles. So these two angles must be complementary. So the two acute angles in any right triangle are complementary. They add up to 90 degrees. So that means the measure of this one down here, ABC, that angle there, has to be 90 degrees minus whatever T is. Now look right here, okay, and this angle here I'm going to claim is going to be a right angle. Well, if you add it up, plus T plus this one over here, which is 90 minus T, 90 degrees minus T, that adds up to 180 degrees. But these two already, the one here at T and this other one here, add up to 90 degrees. Subtract that from 180, that leaves exactly 90 degrees for this. Now we know in a rhombus we get opposite angles are congruent, but we also get consecutive angles are supplementary, and so those are both right angles as well. So in fact, if they're all right angles and all the sides are congruent, so in fact the green thing is a square. Okay, so now let's look at some areas. You've got these four areas which are triangles. The area of a triangle is 1/2 base times height. So each one of these is half of a rectangle that's B by A. So each one of those is 1/2 A times B, and we have four of them. And then we also have the area in the middle that, now that we know that's a square, we know that's just C times C, or C squared. So if we want to find the total shaded area, notice there's no overlap and we've shaded in the whole figure, we're going to get the four triangles plus the square. So that's 4 times 1/2 AB plus C squared. On the other hand, the whole big thing is a square, and it has side length A plus B, so that's A plus B squared. Now let's do a little algebra. 4 times 1/2 is 2, so you get 2AB plus C squared on the right. A plus B squared is A squared plus B squared plus 2AB. Use the distributive property or FOIL to work that out. And now if we just subtract 2AB from both sides, we get what we set out to prove, that A squared plus B squared equals C squared. So that direction is generally called the Pythagorean Theorem. We started with any right triangle, and then we proved that A squared plus B squared equals C squared. So now let's go through the converse. We're going to go the other direction. So suppose we have a triangle with sides of length A, B, and C, like this, and we know that A squared plus B squared equals C squared. We don't know yet anything about the angles. Okay? So what I'm going to do is I'm going to construct another triangle. And here's how I'm going to construct this triangle. I'm going to construct it so that side B is the same length, side DF is the same as AC, it's length B. And I'm also going to construct it so that the two blue sides are congruent, so CD and FE are congruent, they both have length A. But this one I'm going to construct so that it has a right angle. Now what I don't know on this one is I don't know what the hypotenuse is, but I do know that we have a right angle. In the original one I knew the hypotenuse was C, where C squared equals A squared plus B squared, but I didn't know the right angle. So in this particular case we have, let's look down at this triangle at the bottom. Well, by the Pythagorean Theorem forwards direction, right, we know that A squared plus B squared equals X squared. right here. But wait a minute, we also know that a squared plus b squared equals c squared from this triangle, and so c squared must equal x squared, which means, since they're both positive values, x and c must be the same thing. So this must be c. Well, that means that these two triangles must be congruent by the side-side-side theorem, and so corresponding parts of congruent triangles are congruent, so in fact that angle at C was a right angle. So we have proved this both directions. We proved that if you start with a triangle with sides of length A, B, and C, where a squared plus b squared equals c squared, then it has to be a right triangle with a right angle at C. And we also proved that if you start with the right triangle, that we get this relationship, a squared plus b squared equals c squared, where c is the length of the hypotenuse, the longest side. So there's a couple proofs of the Pythagorean theorem and a proof of its converse.